Okay, so as you're going through the probability, gene linkage, and then more probability problems, you can use this to check your answers and also tutorial if you do get them wrong. So again, with guinea pigs, the whole format of what you need to look for is within the first or the second box, I guess. So in guinea pigs, rough coat is dominant over smooth, and black coat is dominant over white. So now we have if males, so now we're going to be organizing the parental DNA. So if males, heterozygous for rough. So I would start organizing this information because I kind of have it for you below in the boxes. So if a male is heterozygous rough, so for texture, big R, little r, and heterozygous black, so black, big B, little b, is crossed. And you could write that together because sometimes, writing the whole genotype, that could be, how you get in the future. So anyways, is crossed with the female homozygous smooth, so that is recessive, so that's mom, and heterozygous black, so the same genotype as dad. What is the probability that the offspring will have the same phenotype as mom, and pheno meaning how many will look like mom? So I'm going to set up my Punnett squares, and I'll just start filling out the Punnett squares, and then I can pull information from it once I'm done. Okay, so what is the phenotype of mom and what is the fraction for this feature? So we're looking for looking like mom, and mom is smooth. So smooth is a recessive trait, so half of them will look like mom for this one trait, so the fraction in 1/2. Then it says mom is heterozygous black. But we're talking about phenotypes, so how many of them will be black? So if I look here, 3 out of 4 will be black. So my fraction is then 3 out of 4. I will then multiply those two together. So what is the probability that the offspring will have the same phenotype as mom? So 1 times 3, 3, 2 times 4, 8. So that is the answer for problem number 1. Then on to problem number 2. In pea plants, the green color, so I'm just going to you can read as we go. I'm just going to highlight the information. So parents heterozygous for both traits, so we're going to have both parents with the same traits, are crossed. Determine the frequency of the 4 different phenotypes of the offspring. So this is just asking how many will appear like you see below. So now I'm going to do color. I will then do the same thing for height. And again, heterozygous. Okay, so yellow is a recessive trait, so that will be little g, and tall is then a dominant trait. So for this, I'm going to look, we have 1/4, 1 out of 4. And for tall, again, it doesn't matter the second because it's a dominant trait. So then there's 3 out of 4. So 3 out of 16 will be yellow tall. So then again, yellow is a recessive trait, and then short is also a recessive trait. So if we look here, you have 1 out of 4 again. And then for short, we only have 1. So 1 out of 16. Now green is dominant, so it's G dash, and now tall is dominant, so that's going to be T dash, but then short is a recessive, so you have to inherit 2 of the recessive genes. So then if I look here, 3 out of 4 have green. So that's going to be for both, so I'm going to write this below also. And then for tall, again, 3 out of 4, so then 9 out of 16. Now for the short, we already saw again, there's 1 out of 4, so then 3 out of 16. So this is when we had 2 heterozygous individuals, so they are both heterozygous, a dihybrid, so we have a 9 to 3 to 3 to 1. So I'm organizing the most frequent, so 9 green tall, and then 3 for either yellow tall or green short, and then 1 for yellow short. So with 2 heterozygous individuals, you'll get this frequency always. So then if you flip the page over, there's going to be a gene linkage problem. And so for this one, what you need to do is you're going to have to do that simple equation where you just add the small numbers together and then divide it by the total and then multiply it by 100. So this is really all that you need to know. So mapping the genes, that was just so you know why we do this. You will not have to map them. So for this, I'm going to take the smallest numbers, add them together. So 48 plus my 52 gives me 100. I'm going to divide them by the total. So 106 plus 94 plus that 100 I already calculated. This is out of 300. So I'm going to take 100 divided by 300 and multiply it by 100, and I will get 33 map units, LMUs, linkage map unit. Are they on the same chromosome or different? They're on the same. So whenever it is less than 50, they're on the same chromosome. And gene linkage is just looking and mapping out genes on the same chromosome. So you're studying genes on the same chromosome, and you can tell they're linked because you see them frequently together. Just like for humans, red hair and freckles, that is a linked, those genes are linked, they're on the same chromosome, so we see them more frequently. So knowing that, you can then figure out how far apart these chromosomes are. So then for gene linkage problem 2, we have our fruit flies, and again, just how far apart are these? So you're going to take the smaller numbers, add them together, so 120 plus 130 gives me 250. Oops, that's supposed to be 50. And then I'm going to divide it by the total, so I'll take 370 plus 380 plus 130 plus 120, which gives me 1,000. I will then divide 250 divided by 1,000, and it gives me 0.25 times 100 gives me 25. So that's the answer for gene linkage. Again, you'll just have to know what is gene linkage, the definition, how to calculate how far apart. And then finally, for probability of pedigrees, we haven't done this much, so this is kind of some practice to go through and also identifying. So looking here, is it autosomal or sex-linked? So again, you can go through and just count how many of what sex, and if you tend to see a frequency in males, this is then sex-linked. And then this is asking a probability question. So what if the affected male offspring from this, so we're looking at this individual here, has a child with a carrier? So if you were to draw the Punnett square, or I'm sorry, the pedigree, this person would be a carrier. So so this is a male, and this male has this trait that we're looking for, and you can tell it's recessive because you can see the parents don't have it, so they didn't show it, but they were carriers, and then is crossed with, I should almost use a different symbol than that, is then crossed with a female who is a carrier. So I'm going to do my Punnett square for this. So X big R, X little r, Y. So this is focusing on only the males. What is the probability the couple's son will be affected? So I'm just going to finish that part of it. So big R, Y, and then X, little r, Y. So they're looking at males. It is a 50% chance. It's not asking you to compare to all the offspring, just males, so that's how I get 50%, because you see one has it, one doesn't. So that's a 50% chance. So then moving on to the probability problem 2, the pedigree. Is this autosomal or sex-linked? Well, I would say it's autosomal because you see a 50-50. It's not one direction. And I would also again say this is recessive because the parents aren't showing the trait and all of a sudden it's just popping up. So if they have to be carriers then, both of them, to then pass this on to their offspring. So then the question, what are the chances that their next 2 children will have this trait? Well, I could figure out make my or I'm sorry, it's not sex-linked. I could make my pedigree to kind of show. So they have a 1 in 4 chance to pass this on to their offspring. But this is making it where it's actually a chance event together. So what are the chances the next 2 children? So saying both children together will have this trait. So you always have to then multiply. So it's a 1 in 16th chance. I hope this practice helped, and if you have any questions, let me know. Thanks.